Hi, welcome to another lesson at EDU Solutions Institute. Now, today we'll be looking at IB Physics syllabus with a continuation of last week's lesson, where last week we focused on torque and moments, right? And we also focused on the principle of torque, right? And the principle of moments. So stay tuned today as we look at angular displacement, angular velocity, and angular acceleration. Now, what is angular acceleration? Or what is angular displacement or angular velocity? Because motion before has just been in single planes, where we have motion in vertical plane going up or down, or motion going in a horizontal plane going to the left or going to the right. Now, motion in a circle or rotating has to be used with different terminologies. It's the same principle, but we have to consider a little bit more. So angular deals with that aspect where we focus on objects rotating or objects spinning, right? So if we look at the first term here, angular displacement, because we know linear displacement has to do with moving from position A to position B, right? Now, with angular displacement, it's an angle that is created when an object is rotating. So therefore, if we take a circle, right, and the object is spinning about this axis at the center, then therefore, if the object had started at this point at t equals 0 time, then it moved at this point in t equals 5 seconds. Then we say that the displacement that this object moves in an angular motion would be the angle that it suspends here. Now, this angle is not in degrees. When we talk about angular motion, we use a special unit for angles, which we call radians. So hence from now, you hear about radians, or we specialize, we shorten it by calling it rad, right? So therefore, if we say that this angular displacement is the angle that is created, right, which means that the object moves this amount of angle from point A to point B. So therefore, the unit that we represent angular displacement with would be rads or radians. Now, let's look at angular velocity, which some books will have it also as angular frequency. And what this is, it tells us how fast are we covering this specific angle in a unit time. So therefore, we say that this is represented by omega, which is this fancy little w here, right? So therefore, if we want to know what omega is, basically, it tells us if we split this into 1 second time interval and its object was right there in 1 second, then it's the angle that it creates there within that 1 second. So therefore, if it was 5 seconds to take here, then that means how much individual small angles were created every second to reach this point in the 5 seconds. And that's what angular frequency or velocity is. And we say that the unit for this would be rads per second. So it tells us how much angle is suspended in every second unit time. And then finally, our definition for an angular acceleration is that it is how fast is it changing its velocity or its frequency, right? So therefore, it's represented by our sigma sign there, right? So in this case, we say that it's the rate at which the velocity here changes to the new velocity that was there. And therefore, it is now represented in a unit of rad per second squared. Now, you should see some resemblance here, because if we look at linear motion, let's use the black marker for linear motion. If we talk about distance in linear motion, the unit would be in meters, right? If we talk about velocity in linear motion, then we say it's meters per second. And finally, if we talk about acceleration in linear motion, we would say that the unit would be meters per second squared. So we see there is similarity, right? The only difference here is that we change the meters aspect to radians, which is the unit that represents angular displacement or angular movement with. Now, finally, before we go, we look at the different formulas we can use in these three definitions. Now, these formulas might look weird and new, but they are not, right? Because they're taken from linear formulas that we have explored in previous lessons. So, like the first one here, which tells us that delta, so the triangle here means delta, so delta theta is equal to omega f plus omega initial over 2 times time. Now, in linear motion, this would have been the formula that S is equal to V plus U over 2 times T, right? So the only thing here that we have done is to simplify this linear equation to make it be an angular equation. So instead of S, we put delta theta. Instead of V, we put omega F, final angular velocity. Instead of U, initial velocity, we put omega initial, which is your initial angular velocity. And time remains the same, and we divide by 2. So if we look at this one here, right, omega F would represent in linear motion as V, final velocity. Omega I, which is initial velocity, would represent it as a U in linear motion, plus, which represents the A for acceleration, and then also T for time. So again, this would be your linear equation, how to find final velocity in a linear motion, right? And if we come over here, this one also is the same, because delta theta is S, omega I is initial velocity, time remains the same, plus half of the acceleration T squared. This was our linear motion equation. And then finally, this one, omega F, we know is final velocity, and we're squaring that. Omega I is initial velocity, squaring that, plus 2 times E delta theta is the S. So, as you can see, there is no new equation here, right? Motion is motion in any aspect that we talk about. But what's different is that the terms that we use, the units that we use, and the symbols that we will use. So going forward, when we're going to do some examples, then you'll see that when we calculate in terms of rotation or circular motion, we will use these symbols instead of our linear symbols of U, V, S. So thank you for watching. I hope you understand a little bit more on rotational motion in terms of these three unique terms. And I'll see you next time. Thank you.